All right, so we are continuing on radiation section. Okay, so within this, we were on a slide or two about further past this, but I just wanted to remind us with this. We have the equation for the emissive power of a black body, okay? So this is the equation, and we see it with different curves down here below it, assuming with a constant temperature. So at 150, 100, 300, so 300 Kelvin, we see the emissive power would have this curve, so it'd be, below there. Okay, where if we work our way over, we see the sun is 5800, so it would have kind of this curve, so it would be across all that. Okay. And if we integrated across all those wavelengths, that equation, we get the Stefan-Boltzmann's constant, temperature to the fourth. Okay, so that's for the emissive power of a black body. It's the equation we've been using. That's what you get. Okay? All right, so the other part we want to use here is we know what the total is, which is that. So that's a total emissive power. But what if we need the fraction that's emitted at different wavelengths? Because we saw that it has different. What if we need to know the fraction here and here, okay, and over this and then over that section? Okay, that'll play a role. You'll see in the next set of slides with materials that have now different emissivities, absorptivities, and that. So, but that's the important part, is we need this fraction at what it's emitting, the percentage of that emissive power over these different wavelengths. Okay, and we can use this F value, and it's tabulated in table 12.2. So basically, the table has values for this curve that you see right here. So we see in this equation that temperature and wavelength are the factors that influence it. Well, what they've done in this table is just created a column that is wavelength times temperature, and then another column that has that factor. Okay, so if we want to know that factor, we have to get wavelength times temperature. So if we wanted to know it at 3 microns and then and then 300 Kelvin, we would get 900 micron Kelvin, and we would go in the table for 900, look for a row that has 900, and get our F value. Okay, so we'd use that now to get our F value. Okay, so that would tell our fraction, and this is a portion of that table. So we said 900, so it would be kind of in here, right? So that would tell us that 900, it's a very low fraction of that emissive power. Okay, so only less than 1%. Okay, let's change the value and say we're at 1800. We get with microns versus times temperature. So we're along this row. Okay, so that tells us though that about 4% is over that range. Okay, so around 4% of the emissive power is from 0 wavelength to whatever wavelength we just used to put in here. Okay, and then over, if we had another one and we chose, let's say it's this column, and it ends up being the wavelength times temperature. Okay, that means from here to here we have about 4% of the emissive power. From here to here would be this value minus this value. Okay, so it'd be about 36% minus 4, so about 32% emissive power between that range. Okay, and then the rest would be after this, so that would be 1 minus 36. So we'd have 64% is at the wavelengths beyond that value. Okay. Other columns, this one is where we can get the actual spectral intensity, because we could just use temperature times the Stefan-Boltzmann's constant with temperature to the fifth and get this value. And then we could also get the max emissive power just looking at taking this value, pulling it off of here, and then using what that individual value here is to get our max. Okay, between those columns, it deals with more of at that specific point, what is that emissive power, and not over the range. This is over the range. This is right at that specific point. All right, so first example within this is 12.90. Consider clear sky conditions for which the direct radiation is incident at an angle of 30 degrees with a total flux based on the area that is normal to the rays of Q double prime direct 1000 watts per meter squared. And the total intensity of the diffuse radiation, I diffuse, 70 watts per meter squared steradians. What is the total solar irradiation at the Earth's surface? So a little bit of this deals with some of the slides we'll see later on, but it's not so difficult a problem we can't solve already. Okay, so we have a direct portion coming from the sun, and then we have a diffuse portion, and that's kind of what's been diffused through the atmosphere. Okay, so it creates this kind of diffuse portion that is coming in all directions, and then we have the direct portion that's coming in a very specific direction, and that gave us 30 degrees, okay, from normal. Okay. All right, so that just means our direct. We take our direct value and we have our 30 degrees, okay? And then for our diffuse, we just have pi times that diffuse value because it's over this whole hemisphere, right? So then we just use pi. So it's a nice simple equation that ends up happening. So we get that 1000 and then 0.866 comes from the cosine 30. And then we have that pi steradians, and then this. So we add those direct and diffuse together, and we get the total, which is 1086. Okay. All right. Another example is 12.14. Let me flip to it. The energy flux associated with solar radiation incident on the outer surface of the Earth's atmosphere has been accurately measured and is known to be 1,368 watts per meter squared. The diameters of the Sun and Earth are 1.3 times 10 to the 9th and 1.27 times 10 to the 7th meters, respectively. And the distance between the Sun and the Earth is 1.5 times 10 to the 11th meters. Part A is, what is the emissive power of the Sun? Part B is, approximating the Sun's surface is black, what is its temperature? Part C is, at what wavelength is the spectral emissive power of the Sun a maximum? And then part D is, assuming the Earth's surface to be black and the Sun to be the only source of energy for the Earth, estimate the Earth's surface temperature. Okay. All right, so we see the schematic here, which is the problem's drawing. We have the Sun, gave us the diameter of the Sun, okay, the diameter of the Earth. We have the distance from the Sun to the Earth, okay, from the center to the center here, and that was given. The other thing they gave us was that the solar radiation on the outside of the Earth's atmosphere, this value they gave us is 1368 watts per meter squared, okay? So I think that's everything. And then they have some assumptions that'll play in as we go. So first off, they want the emissive power of the Sun. So what's the emissive power of the Sun? What's being emitted, right? So that would be In this case, it's going to be watts per meter squared still. And then we have the surface temperature of the sun, wavelengths at the maximum solar emission, and Earth's equilibrium temperature. So we'll start with the emissive power of the sun. Okay, so it's asking for power, right? So the only thing we have right now that deals with power is this solar radiation incident at the outer surface of the Earth's atmosphere. So this value is what's happening right there. Okay, well, we can take that value and back calculate from conservation energy what it would be when it leaves the sun's surface. What's happening is we have a sphere, right? You have the sun is a sphere, right? And then if we take this as another big sphere around it, okay, the energy that's emitting off of the sun gets spread out as the surface area increases bigger and bigger. Conservation energy says the total energy is the same, right? But the flux will change because that's watts per meter squared, because the area is getting bigger as it goes to just emits off of this bigger and bigger sphere. Okay, so that's what we're going to utilize to get the emissive power right here that's leaving the sun's surface. Okay, and we're just going to do the COE on these, basically these two spheres. We have the sphere here and its power coming off of it, and then we have the sphere here and the power that we have that was measured there. Okay, so we need then surface areas. Okay, and this is where it comes into play. We have the emissive power we want at the sun's surface, and then we have the surface area of that sphere. Okay, so this is sphere surface area, and that's the sun. Okay, it has it with diameter, but it's still a sphere's surface area. Okay, even though it's using diameter there. And then over here, that is also a sphere's surface area, but they're using radius instead. Okay, and that is the larger sphere, right? That's this big sphere we're looking at right here. And what that is we have to just modify it a little bit because we don't have that distance. We have Earth's diameter, and then we have the distance between here to the center of the Earth. So that's why we have this subtraction right there of the radius of the Earth. Okay, and so again, surface area. We know this. We know all this geometry, and so then we can calculate what that emissive power per meter squared of the sun is, and we get this value. Okay, so it's very much higher. You know, we have here's 1368, which is about 10 to the third, right? And this is 10 to the seventh, and that's all because that surface area is getting bigger and bigger as it's projecting out. Okay, so at the sun, it has that emissive power, the surface of the sun. That's part A. Part B. And now the surface temperature of the sun. Okay, and this is where we take into account one of the assumptions they told us to say. The sun is a black body, and emissive power of a black body is just Stefan-Boltzmann's constant, the sun's to the fourth. Okay, temperature of the fourth. Right, black body is when you have the emissivity is 1. Right. So if we already have the emissive power, what's coming off of the sun right here? So we solve that. We have the constant, and so all we have to do is solve for the temperature, and we get 5790, right? If we go back to our slide right here, it says the solar radiation is 5800 Kelvin. So that's very close. We had 5790. So that's very close, right? All right, then part C asks for the wavelength of maximum solar emission. And that comes back to that slide again. The maximum is right here, right? So if we projected that down, it'd be right here, okay? We also have this line that's connecting the maximums. This dashed line you see, right? And it has this equation to it, okay? So if we want the maximum, for ours, we just put in our temperature and solve. You can also see it here. This stays the same. If we want this value, all we have to do is put in our 5790 for this and divide 2898 by 5790 Kelvin. And that's what you see right here. Okay, and it becomes 0.5, which is also approximately what we would see if we just read this point and projected it down here on the x-axis. Questions so far? All right. Part D is the Earth's equilibrium temperature. Okay. Let me also write this as COE. Okay, and then Earth's equilibrium temperature, we're going to also do another COE. And we're going to basically look at the Earth. And we're going to say energy, this is E in minus E out is equal to 0, right? Steady state. Okay. Out is the emission. Okay, so this ends up being E, what we're emitting. Okay. And then in is what's coming in from the sun, right? So that's our solar portion, and we're neglecting any atmospheric influence. Okay, so if we look at this, this is on this equation over here, this ends up being the E, and this is from the sun. So that's what's coming in. So emitting, the emission of the Earth is that. And then here's the area it's emitting over, and that is the sphere surface area again of the Earth. Okay, and then the sun's energy that's coming in, this is where it becomes a little tricky. If you go back to our first slide here, so it's coming in right here, and then it hits the Earth on that projection right there. So the only thing that's coming in is this energy. Once it hits there at the Earth's atmosphere, it's coming in, but it's on a projection of just a circle. If we were to look at what's coming in, it's just going to be a circle, because the other side of the Earth is dark, right? So we just have that energy that's coming in, and so that means this area is a circle, because the sun just has its heat flux that's coming in on that projection of that circle on the one side of the Earth, right? Last equation we have then is the emission of the Earth is again emissivity, Stefan-Boltzmann constant, temperature of the Earth to the fourth. And the emissivity is 1, because again we're assuming black body. You see that assumption right here. Okay, so this equation, we're looking for the temperature. We have emissivity, we have Stefan-Boltzmann constant. So if we come up here, then we have an equation for that emission. We have all these diameters. We have that heat flux at the outer atmosphere, which was given to us in the problem. So then solving those two equations for the temperature of the Earth, we get 279 Kelvin is the average Earth's temperature. Okay. So this is kind of like what that conservation of energy looks like schematic wise. The Earth's emitting all around it on that sphere, but it's the sun's heat is just projecting on that area. Questions? All right, so within now the next section of slides, we're taking and looking at the properties, okay, and the assumptions we can make with it, because we haven't really talked at all about emissivity, absorptivity, transmissivity, and reflectivity. We related them in the last class, but we now need to get a value, right, for a surface. And then we also looked at just a black body where the emissivity is 1, right? And the absorptivity would have been 1 too if we used it for a black body. So now we need to figure out what it is for any other surface, okay? So if we first start with the surface emissivity, okay? Its property, okay, the ideal one again is for a black body has an emissivity of 1, right? So if we're looking for any given surface, it has spectral and directional, right? So here's our direction, and then temperature plays a role too with the emissivity, right? So here on the denominator is that black body value, and here's what you're getting actual emission. So here's what we have actual for that surface, okay? Now if we take a directional average, basically integrate over the direction, now we have just the wavelengths and temperature influence, okay? Again, it's black body over actual. And if we're now looking for total hemispherical emissivity, we can integrate over the wavelength, and that's what you see being done here, over this wavelength, and compare it to the total that a black body would have, because it doesn't have any changing in the emissivity, it's always 1. And that'll get your emissivity at any given temperature, okay? We can also, if we measure properties, take the normal emissivity and set it to the total, and that's what you see here. All right, below in these, we see the total normal emissivity for some different materials to kind of give you an idea. So here's metals, right, all right here. And we see surface finish being something that changes things a lot. So highly polished metals, we see we have this low emissivity of not quite 0.1, and then below that. Okay, as you get polished, it's a little higher, as received, higher, and then we can see if it's oxidized, we get this large range. The surface roughness and what it looks like there has a big play in your emissivity, right? And then we have some other materials like ceramics. Okay, we have special paints, very high emissivities. We have water, skin, high emissivity. Right, and so we have large, in general, kind of large emissivities with non-conductors, and then polishing has low emissivity where it increases for unpolished and oxidized. if we kind of look at now, this is kind of overall the total, right? If we kind of look at a wavelength influence, so this is the spectral, okay? So wavelength of emissivity and how that emissivity of these different materials change over wavelength. You see there's a big dependence, especially, let's say if we looked at aluminum oxide here, this has a very large change in emissivity depending on whether you're at low wavelengths here or high wavelengths here, right? Or stainless steel polished, how it's still, you know, low or a high emissivity, higher emissivity at low wavelengths, but very low emissivity at high wavelengths. Okay. And then we have tungsten. We see the different temperatures kind of curve where it changes at higher wavelengths gets lower, but it changes with temperature a little bit. And then if we just look at temperature, which we kind of already did with tungsten up above, but you can see how temperature will influence it for the total emissivity. So that's integrating over wavelength at each of these given temperatures. We see this curve, we see stainless steel curve, stainless steel oxidized versus polished. And then if we look at aluminum oxide curve down, silicon carbide, so we see this conductor versus non-conductor kind of relationship here. All right, so we kind of talked a little bit about this in the last class, but we can, of the absorption, reflection, transmission. So irradiation coming in, it can get reflected, bounce right back out. Doesn't even go into the surface, right? It's just bouncing right back out. It can get absorbed, okay? So that becomes energy inside our medium there, or it just transmitted and it just isn't any energy that actually ends up inside our, in this case, our medium, okay? So it radiates, it gets reflected, absorbed, transmitted, right? What we're seeing here, though, is at any given wavelength, you can relate these, okay? That means you can also relate the properties. At any given wavelength. Because if you have a certain wavelength coming in, it's going to either get reflected, absorbed, or transmitted. So before we looked at it as the total one, which we can relate those, but here at an individual wavelength, we can relate those too. Okay. And then we saw opaque material, there's nothing transmitted. Okay, it doesn't transmit through. And then here's an interesting question that we can ask ourselves when we see these later slides. Are water and glass semi-transparent, or are they opaque, right? Well, we'll see what happens, okay? All right, so absorptivity. So this now deals with stuff that's coming in, right? Emission was, that we just talked about, was anything that any surface like your table has a temperature over absolute zero, it has emission. It's emitting radiation, right? Now we're talking about what's coming in, surface irradiation. That could be solar, that could be a heat lamp, it could be another very hot surface that you bring near another surface. Now it would be creating some radiation that's going to hit that other surface. So this now deals with what's coming in, right? Well, with absorptivity, we can look at it just like we kind of with these equations, like we did with emissivity. We have what's coming in, we have our perfect absorber, and we have directional and spectral. So with direction, we have influence, and then with wavelength, we have our influence. And then we see if we integrate over direction, we just have spectral, right? So then we just have wavelengths. Okay. And then total, so that's now integrating over those wavelengths, we have the total, right? So now it doesn't have that subscript on it at all. And this will play a role in see it in these equations. Okay. Reflectivity, similar again. We have spectral and directional, so we have wavelength and direction. Okay, if we integrate over direction, we just have wavelength, okay, which we see here in our subscript. And then if we integrate over the different wavelengths, we see that we have the total. Okay. All right, so here is the spectral, right? Spectral, so at different wavelengths, right, of absorptivity and reflectivity, okay? And this is opaque surfaces, so nothing's getting transmitted. So that means if you're at 0.8 here, you're at 0.2 here, right? Because we're basically relating those two together. Okay, the total of what's coming in is either getting reflected or absorbed, okay? All right, so what do we got here? So if we look at that, we can take a look at, let's take white paint for our first look at this. We have white paint has a lot of reflectivity around here in these wavelengths, and then it drops, okay? So at these higher wavelengths, it's got a low reflectivity, very high absorption, right? But at the low wavelengths, it's very high reflective and very low absorptivity, right? And we can also look at, say, snow, right? It's also has this kind of dependence here of wavelengths, low versus high. Okay, so it really depends on what wavelengths is hitting it or what it's dealing with, whether it's a low wavelength or high wavelength, on what it's going to experience, okay, with reflectivity or absorption. And you can see other materials showing different properties for that too. We have transmissivity, so what would be getting transmitted through? So it's not going to play a role in changing the temperature of that material because it's just transmitting through. Okay, this is the energy that just transmits right through. So we have this equations, which we have here is spectral of absorptivity, right? So we have wavelengths, and then we have that question of where is it? Are glass and water semi-transparent or opaque? Well, let's take a look. Here's glass, right? So we have glass, low wavelengths, very high transmissivity, and then all of a sudden around 3, we get it dropping. Okay, so now we have that it is very low transmissivity at high wavelengths, or we had other things. But so it shows whether it is wavelength dependent, right? We have this low wavelengths, high wavelengths. So it really depends on the wavelength whether you can say it's opaque or semi-transparent, right? So it's transparent around those wavelengths where it has a high transmissivity, and it's opaque where if it has a low transmissivity. In some of these materials, it changes depending upon the wavelength. Okay, here we see high iron glass changing rapidly. Okay, when you get to the potentially you might do the solar water heater in your thermal lab. It has different, so it deals with radiation, solar energy coming in, and there is a solar. We have 3 different solar water heaters, and there's one with a glass on it, okay, as a protective for convection. But that glass, if you're doing solar water heaters, or if it's on a solar water heater on someone's roof for maybe solar water heating their pool or something like that, that glass you want to transmit solar radiation through the glass, right? You want that solar energy to come through the glass and get transmitted through, okay? And that occurs at low wavelengths, right? But this piping that you have in there that has the water running through it is also emitting, right? Because you have what's coming in, and then you have what's emitting, right, on that pipe. And you want emitting, that pipe's going to be at a lower temperature than the sun, so that now will have high wavelengths. So you want now it to not transmit, because you don't want it to lose radiation from the pipe. So you want it to allow solar low wavelengths, the solar radiation to come in, but you don't want it to let your emission of that pipe leave, right? Because if we go back to that figure again, if I can get there, here it is. Come back to this a lot. We have if our pipe running through is 300 or close to 300, it's going to be emitting between above 2 microns in wavelength, right? So then the properties below that pipe, you don't want to lose that emission out back to the atmosphere. So you don't want it to be able to transmit through the glass, okay? So you want that to be low. Versus solar has, it's 5800, so most of it is at this low wavelengths. So you want it to transmit through the glass. Otherwise, if it was just heating the glass, reflecting off the glass, you wouldn't get to that pipe, right? So that's the difference in these kind of wavelengths you see between solar, which has a 5800 Kelvin source temperature, and the surface of something around 300 Kelvin. All right, and we can relate those properties, right? So if we have transmissivity and we get absorptivity, that means using this equation of the plots. So if we have this plot and we have reflectivity, we can get absorptivity for a semi-transparent material, okay? So we have both of those equations. You have kind of the overall and then at any given wavelength, right? If we want the total hemispherical transmissivity, we just integrate over the wavelength, and that's what you see down here. All right, so now we get into play with the assumptions we can possibly make. So here's Kirchhoff's law, okay? And first off, if we can equate the emissivity, the total, right? So this is total of emissivity at absorptivity, right? This is a surface, this is emissivity, which deals with emission, and absorptivity, which deals with irradiation, what's coming to it, right? To make that where they're both set, it's very highly restrictive, okay? So that means the surface corresponds to emission from a black body at the same temperature. So that means both of the surface temperatures are the same. Kind of what's the source of irradiation and the source of emission are both black bodies and both the same temperature. Okay, so that's very restrictive. Okay, the next one, which is less restrictive, okay, which we can use without restriction, is that the spectral and the directional values are the same. So this has, right, wavelength and direction, okay? So without restriction, we can say those, at any given wavelength and direction, the emissivity of a material will be equal to the absorptivity of that material, okay? We have now some more things that we can possibly equate, and that's with Kirchhoff's law. If we are gray, diffuse gray surfaces, if we take this further. So we have the equation for emissivity with wavelength at any given wavelength. We have absorptivity at any given wavelength. So when can we set the emissivity at a given wavelength equal to the absorptivity? Okay, and it's basically comparing these two equations. So when can we do this? We can do this when one, the irradiation is diffuse. So that would take this term and pull it out of the integrals. If it's diffuse, it's the same. It doesn't have any directional influence. And if you do that, the equations look the same. Okay. The other is if the surface is diffuse. Okay, so that is now makes us be able to set the emissivity equal to the absorptivity at any given wavelength. So that's a big one here. So diffuse, okay. All right, so that's with wavelengths at any given wavelength. What can we do to make the total emissivity equal to the total absorptivity? Okay, so when? Okay, that's again comparing this equation to this equation. Okay, and one is Blackbody at surface temperature, so the temperatures are the same. Two is the more one to get here. We have gray, surface is gray. Okay, and that's where the absorptivity at a given wavelength and emissivity at a given wavelength are independent of wavelength. So what does that mean? And that's what these figures are going to tell us here on the right. Well, we have a plot that at any given wavelength, the emissivity is equal to the absorptivity. So we have cross here over all those different wavelengths. They're the same at a given wavelength, right? Those two properties. Well, here we have, this is our irradiation. So that's what's coming into our surface, right? And then we have the emission. That's what's leaving our surface. Well, when we look at this for emission, it's over these two wavelengths that it's missing. Emission is occurring between those two wavelengths, right? And for irradiation of what's coming in, it's over these two wavelengths. Okay, so it's at different ranges of wavelengths that it's irradiation versus emission. But if we look at the properties here between the lowest and the highest, so we look between this one and this one, 1 and 2 is that, and between 3 and 4 is that, and we see the emissivity is equal to the absorptivity. Even though they're occurring at different wavelengths, over different wavelength ranges, that is a gray surface, okay? Let's say, give an example where it isn't. Let's say this emission was occurring here instead over this wavelength, okay? Well, here has a value down here, right? And the irradiation is up here. So you can see that the properties are not the same now, okay? Even though they're at different wavelengths, the emissivity and the absorptivity are going to be different, okay? Where over this and this, even though the wavelengths were different, they were over that range, it was independent, okay? The emissivity and the absorptivity were independent of wavelength over those ranges. Okay. All right, examples here. We have 1238. Any questions so far? All right, 1238. The spectral hemispherical absorptivity of an opaque surface is as shown. Okay, so we have this figure that's shown. What is the solar absorptivity? Okay, so that's one question. If it is assumed that the emissivity at a given wavelength is equal to the absorptivity at a given wavelength, and that the surface is at a temperature of 340 Kelvin, what is the total hemispherical emissivity? All right, so first off, you see the figure that's given. We have wavelength and absorptivity, right? All right, so we have wavelength and absorptivity, right? And it's at a given wavelength. So we see it's got a couple steps here. So we have a different value from here to here, from here to here, and then here to here. So this is a much nicer figure than, say, if we were looking at absorptivity back here, right? So these values have all these different steps, right, in between each of the data points. But if we can understand what to do for this, we could take it to a much more data points and much more step changes in that data if we needed to. Okay, so we'll really be looking at more of a simpler, what we see here. Okay, so first off, we need to find the solar absorptivity. Okay, all right, but we have how the absorptivity changes with wavelength for the surface, but we need to know how it deals with if it has solar irradiation coming in. Okay, and that deals with the emissive power of solar radiation. Okay, so if we go back, it's on the other set of slides, but that's at those low wavelengths, right? All right, so let's go through our steps. So we want the solar absorptivity, right? So that deals with the absorptivity at a given wavelength and the emission of that source, that irradiation, which is the sun, at that given wavelength. So we're integrating over that and comparing it on the denominator is the black body, because its absorptivity is 1. So that's why you just see over that. So we're integrating over all those wavelengths. So across this to infinity. And with our material, though, we can basically break this up and go between here to here, because we have a single value. We can go from here to here, and then you can go from here, and basically it goes onward to infinity, okay, wavelengths. And that's what you see below. We can break this up, and that means we can pull this out for each integral section. So if we're just looking at this section, this section, this section, we want, and we can utilize this ratio right here of the emission at that wavelength over what it is for the black body. Okay, so that fraction, so this is the total, right? And this is over that section. Okay, so we're looking, and you see below it's that factor F. So that comes into play, that first set of slides we looked at. I'm switching to that right now real quickly. Again, we're looking at that emission, because it's solar, it has this whole big emission portion right there. and we need to look at the fraction that's being emitted with the absorptivity of the material that we were given, okay? And this is that fraction, right? We have F we can use, okay? Where we're looking at that integration over that wavelength over the total, okay? Oh, it's on the other side of the slide. And we break it up into 3 sections. Okay, so that means we have our first section is this, right here. This is the fraction of solar irradiation times that absorptivity, okay? Here is over this section, second section, which is 0.9, over the fraction of what's coming from the sun over those wavelengths also, okay? And that means you're just taking the fraction from 0 to 1.5, 0 to 0.3, subtracting it. The difference between those is what's going between this section, okay? And then the last is this value of absorptivity, and it's everything else that's being emitted, the rest, okay, from the sun. And we look up in our table for each of these factors then. So to get from 0 to 0.3, we just look up the factor 0 to 0.3. That requires 0.3 times the temperature of the sun, which is 5,800, so we get this value. And we go and grab F, and it's about 3%. Okay. The next step is from here to here. And when we go and grab it from the table, it first grabs this, we want to get at 1.5, so we're getting everything from here to here and then subtracting off how much was from here to here. So 1.5 is a whole fraction, which ends up being about 88% when we do 1.5 times 58, grab this value and go get F from that table. We get about 88%, and we subtract off, so this is 0.88, and then we subtract off our 0.03, so about 85% of that irradiation is come from the sun, is coming between those two wavelengths, okay? So 0.9 is going to play a heavy role in the overall total absorptivity for the solar. And then the rest, so the 12% that's remaining, because this is 1 minus 0.88, is at this value, okay, 0.1. Okay, so if we put those together, okay, here's our first section, which was 0, and we have 0.9 times that fraction, 0.1 times that fraction, we get 0.774. Okay, so that's the absorptivity of the solar portion of what's coming in. Okay. Then it asks, part B is the total hemispherical emissivity. Okay, it also told us, and the temperature of the surface was 340. Okay, and it also told us to set this equal to this. Okay, the emissivity at a given wavelength to the absorptivity at a given wavelength. So that is diffuse. That's what it's telling us. That the material is diffuse, which means this is equal to that. So the same curve here is we can utilize for the emissivity. The thing that's different is the source is the surface for emission, which is at 340. And if you're thinking about the surface, it's emitting, and the source right here, the temperature is 340. The irradiation that's being absorbed from the sun, its source is at 5,800 Kelvin. Okay, so that's why we use 5,800 Kelvin. Here we're using 3,400. Okay, so the fraction F now deals with the temperature at 340. So when we're doing the wavelength times temperature, we have to do it for each of these 0.3 times 340 Kelvin, 1.5 times 340 Kelvin. They're skipping a step here. We could do the, also do where we have 0.3 times 340 and get its value. What they've noticed is even at 1.5, there's no emissive power when you're at 340 Kelvin, okay? Because it's at high wavelengths. If we look at our figure again, let's go skip back to it again. So this problem says 340, right? Well, if we look at this figure again, .340 is right, just slightly bigger than this curve, but we can just say we're here. We see it's not even has that surface has only emissive power that's starting at a wavelength of 2 microns, right? Well, the material properties, when we're looking at this curve right here, has 1.5. So everything over here doesn't matter about its material properties on the emission side of it, because that surface at 340, it's only going to really have emission occurring with that wavelength at the end, which is 0.1. So that's why you see this factor when you go look it up in table 12.2. You just get that it's 0 that's being emitted at wavelengths of 1.5340 Kelvin. Okay, so that means everything's being emitted at a higher wavelength. So that's where everything's just 0.1 then for emission. So you see it's 0.1 for emission on that surface because the surface is at 340, and the solar absorptivity is 0.774. Okay, so they're very different because the source of that radiation temperature is very different, right? So when you have solar, which is a very different temperature than the surface's temperature, you have these very different property values between absorptivity and emissivity. So that although we could make that this was equal to this, we can't say that this is equal to this in this case, okay? Because of the different wavelengths that the emission versus the irradiation is occurring at. All right, next problem. Any questions? I move on. Okay, next problem's 12.7.7. And this is something we could have saw in chapter 1, except for getting the properties. Okay, that's the new part. Okay. All right, so 12.77. The thin-walled plate separates the interior of a large furnace from surroundings at 300 Kelvin. The plate is fabricated from a ceramic material for which diffuse surface behavior may be assumed, and the exterior surface is air-cooled. With the furnace operating at 2400 Kelvin, convection at the interior surface may be neglected. Okay, and they give us this figure you see. All right, part A is if the temperature of the ceramic plate is not to exceed 1800 Kelvin, what is the minimum value of the outside convection coefficient, HO, that must be maintained by the air cooling system? Part B is compute and plot the plate temperature as a function of the convection coefficient. Okay, so part B is just a parametric study, changing the convection coefficient, seeing what the plate temperature, how that changes it. All right, so we have this furnace, right? It has 2400 wall temperature. We have this ceramic plate that we're honing in on. And then at 1800 Kelvin, we have the surroundings at 300, okay? And they also give us the absorptivity as a function of wavelengths, right? But it only has one step. It goes from 0.3, and at 3, go to 0.8, okay? Well, we need the outside convection coefficient. So to start out with, we're just going to look at and zoom in on the ceramic plate here and do our COE like we did way back in chapter 1 even, okay? We take our plate, we have steady state and told us to neglect convection on the interior surface. We're going to make the furnace cavity and the surroundings are large, okay? And So we go through, right? We have our plate right here. We have our boundary around it. And what's coming in? We have the furnace, and then the absorptivity times it of what's going to make it an energy inside that plate. We have the plate itself on the left emitting, so it's above 0 Kelvin, so we know it has emission, right? So on the right side of the plate, it's also emitting. Again, plate's above 0 Kelvin, so it has emission at whatever temperature it's at, which is 1800 Kelvin in this case. And then we have irradiation coming in that gets, some of it gets absorbed on this opaque plate, and it has an absorptivity with it. Because of that, some of it gets absorbed. And then we have convection on the outside surface of the plate. So we have a bunch of different energies. From our boundary, we just now set up our COE, now from our schematic, and just put it in equation form. E in minus E out, 0, right? So we have what's coming in from the furnace side of radiation, the energy that it makes it into the plate. Okay, the remainder gets reflected, and we don't care about that. That's just reflected, right? There's nothing transmitted because it's opaque. On the right side, again, we have the surroundings has irradiation, and that's the portion that gets absorbed into the plate. And the rest off of the surroundings just gets reflected. And again, nothing's transmitted because it's an opaque plate. And then the plate has some temperature, so it's going to have emission because it's at some plate temperature. So it'll have emission, just like the table you're sitting at, the walls around you, whatever it is, it's emitting if it's above absolute 0. Okay. And then we have our convection, which we'll just use Newton's law of cooling. All right, so we now put, our equations in there for irradiation with the Stefan-Boltzmann constant, temperature of the 4th. So this comes from the wall, surroundings, the surface plate, right? And then we have Newton's law of cooling. Okay, area of the plate is removed from all these, so it's just divided out. Okay. All right, so we look at this and just COE, something we could have saw before, but in something like this before, they would have gave you all those properties for absorptivity and emissivity. Now, they just gave us this, okay? This figure we see for how the temperature changes. Actually, they just gave us this, right, with absorptivity. It equals emissivity because we're going to assume the plate is opaque and diffuse, okay? So because it's diffuse, we get to say at any given wavelength, the absorptivity is equal to the absorptivity. The emissivity is equal to the absorptivity at any given wavelength. All right, so we need to figure out our properties. If we rearrange this, we have all the temperatures, though, given our constant, but we don't have our emissivity, right? Constant, we have our surface temperature, our surroundings temperature. So we don't have this, we don't have this. Okay, so we got to get those 3 properties. Okay? And the big trick in any of these 3 properties is they depend upon the temperature they're with. This one depends upon this temperature, this one, and this one, this temperature. Okay, so rearranging for the convection coefficient, we have our equation right here. Okay, so we need to get all these properties. So if we start with what's being shown, the plate total emissivity. Okay, and we just have to look at the emissivity right here and how much fraction of emissions occurring over that section, and then the emissivity here, which is 0.8, and how much fraction of emission is occurring over that section. All right, so we do that, right? So we have our 0.3, we have our 0.8, we got to get our F factor from our table, okay? And it's the plate, right? So it's the surface temperature of the plate, which is 1800 Kelvin. It's TS, okay? And then 3 is our wavelength where we have the jump. Okay, so 3 times 1800, we get 5400. And then from our table 12.2, we see that 68% is an emission is occurring from 0 to our given wavelength 3 at 1800 Kelvin. So that means the remainder, which is 32%, is occurring at above wavelengths of 3 at 1800 Kelvin. Okay. So we have then 0.3 times that factor is 0.8 times our, basically it ends up being our 0.32, right? 32% that's remaining. And we get our total emissivity that we can now put in there. We need to do the same process for the two absorptivities. Okay, so for the plate, due to the furnace irradiation. Okay, so this is absorptivity, irradiation, furnace. So again, we only have that one break of 3 microns, but the temperature of the furnace is at 2400 Kelvin. Okay, so it's 3 times 2400, so we get 7200, and our fraction is now 0.82, right? So this is table 12.2. Okay, and that we do the same process and we get 0.391. Here we do it for the plate absorptivity from the surroundings, and the surroundings are at 300 Kelvin. Okay, so 3 microns times 300, we get 900. And that from our table for the factor F is 0. So that means it's all at very high wavelengths that it's occurring. So 0.3 times 0, and then it's 0.8 times 1. So we end up just with 0.8 for that absorptivity. Okay, so we have all our factors. We can plug it into our conservation of energy equation, and we get 126. Okay, here they're just changing that H value and seeing what the plate temperature changes to. Right, we were right around here in the part A, and now they're just varying it and seeing what's occurring. Any questions? Okay, so there's one little set of slides we'll get through today, and then we'll do an example next class. This just takes what we learned in these other slides and just applies it to some of the more specifics for solar. And we've talked a lot about what's in here already, so that's why I'll be able to go fast. Solar radiation, we already talked about it, right? It's like a black body at 5800 Kelvin. We already looked at kind of spherical of the sun, diameter, distances, we already talked about. One other thing that we can have is the solar constant, where we already used this solar heat flux of 1368 in one of the previous examples. And there's kind of, for eccentricity in the Earth orbit, we can modify it slightly. Okay, we have also any angle that we're looking at, which is what we did in the example, that direct portion from the sun. We took SC, multiplied it times cosine theta, and then we got our direct portion. Okay, so that's the direct. But also we get interaction with the Earth's atmosphere from solar radiation. So there's absorption by aerosols, by gases at different wavelengths, and scattering. Okay, and you can see that here with kind of scattering occurring. And then that scattering then puts off different values of radiation when they're scattering like that. Okay. All right. So here's kind of that big picture I've been kind of honing in on and talking a lot. Is solar radiation is at that 5800. It occurs over low wavelengths, right? Short wavelengths, where Earth's emission is over long wavelengths. So you see from 0 to 50, and most of it's over this high wavelengths. because it's near 300 Kelvin, in this case 290 Kelvin, right? So you have the short wavelengths for solar radiation, long wavelengths for what the Earth is emitting. And you can see what that is at 5800, and then how it is extraterrestrial, and then how these Earth's atmosphere kind of absorbs different wavelengths. We have ozone, water, showing CO2, different things changing what actually ends up hitting the Earth's surface. Same here of what's emitting out. This is kind of the parameter there. And then at the Earth's surface is this. And then you see what hits the outer portion of the surface because of ozone and CO2. And we can also look at an energy balance. So this is at the outer edge of the surface of the Earth's atmosphere, and then at the Earth's surface. And here we see short wavelengths. So this is what's coming in kind of from solar. So what's coming in and how it gets reflected, gets sent back, what makes it to the Earth's surface, what gets scattered and absorbed, right? There's different portions of that, what gets reflected off of the surface. And then we have what's leaving this Earth. You know, some of that now gets absorbed in gas and particles, and some of that then makes its way back from those gas and particles. Some of it makes its way out to the atmosphere. So you see these different kind of components that's going on here. So again, the 5800 from the sun, we have extraterrestrial at the outer portion of the atmosphere, and then you have on the Earth's surface what makes it there. Here is that solar radiation. We already used this kind of equation though, is the direct portion and the diffuse portion in that example earlier on, where we had the direct, had that cosine theta, and then the diffuse portion had the pi times that diffuse factor. And what's direct versus what diffuse really depends upon whether you have clear skies or overcast, right? If it's completely overcast, you're really not seeing any direct solar hitting. It's coming from that diffuse portion though. Any surface that's over absolute zero has emission, right? So that means the Earth's surface has our emission equation, okay? A lot of the Earth's surface deals with these materials. So they have high emissivity. You can find all these in these appendices, but oil, sand, water, snow, concrete, asphalt, all have very high emissivity, which is, you know, a lot of what the Earth's surface is covered by. So we have that, what's emitting off the Earth, okay? We've already done this where we approximated the atmosphere with as a black body emission. So when we were looking at E earlier on, and we did let's make this a little better. So we have the surface to the fourth, but then we had where we had kind of the sky to the fourth. We subtracted that off, and that's what you're seeing here. That's this portion when we did that subtraction off, because this is what's leaving, and this is kind of what's coming back from the atmosphere, high in the sky, okay? And that sky temperature changes based upon the conditions, right? And this is far in the sky, not just right off the Earth's surface, right? And it changes dependent upon, you know, the environmental conditions. And we kind of already talked about kind of these properties of reflectivity, absorptivity with these, you know, low wavelengths versus high wavelengths. So the high wavelengths from the sun, low wavelengths from the Earth, right? Last slide. If you have something, depending on what you're trying to do with that solar radiation, depends on what you want on the surface properties. Let's say you have a refrigeration truck, right? Well, a refrigeration truck, and that's your surface, right? You have solar coming in, and then you're emitting off, right? Well, in a refrigeration truck, you don't want to collect much, right? So you want to keep and reject energy. You don't want to collect that energy from the sun, right? So you want this ratio here to be low, because you want to be rejecting energy a lot, but you don't want to be absorbing anything, right? Because this ends up being this. So you want low absorption, right? So that means we're going to want to reject. So that means we want these. So that, see, you might have your refrigeration truck painted white because of that, okay? Where collection, you don't want your refrigeration truck painted black, because now that means your emission is low relative to your absorption. So now you're going to have a high absorption, and now so more energy is going to come into your refrigeration truck from that solar, okay? Where maybe if you're collecting and you're looking at trying to get that solar energy into something, solar collection, now you want that emission to be low, right? So you want that to be low, because you don't want to lose that energy, and you want the absorption to be high. So that means this ratio, you want, you know, something that with that high ratio there for collection, okay? All right, that's it. So we ran out of time. We'll do one example, which looks a lot like all these other examples. Next class, okay, any questions? You guys were pretty quiet today in this section. I'm just going to take it as I have the most excellent lecture ever, right? You guys were enthralled, understood everything, and I'm elated. But
that's exactly how it was, yeah.
But if it wasn't, please don't hesitate to ask or contact me through email. And then also when we get to that example, please ask as we go through, okay? All right, so that's it for today.
Okay, thank you.